In a previous video, we realized that arc length, the length of a nice little curvy arc, could be determined by just finding the distance between points on that arc. So I could find the straight line distance here, 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 and there. And to make it more accurate, you take more of these little distances. The smaller those widths are, the more accurate it's going to be. Every curve is really just the combination of lots of little tiny straight lines. At least that's what your television set will tell you. As it comes out this way, this is our distance formula. So we just need to find the distance formula, and we need to add up an infinite number of them. So let's just do some mental gymnastics here. Let's see. I think in calculus terms, the x2 minus x1 is just the same as the change in x, and y2 minus y1 is the same as the change in y. Watch this next step carefully. So this next step is we're going to multiply by 1. We're not changing anything, we're just multiplying by 1. However, dx is the same as the square root of dx squared. The square root of dx squared is just dx. So I'm writing an equivalent statement here. And when I divide dx squared divided by dx squared, I get 1. dy over dx squared is nothing more. Wait, dy over dx. Where have we heard that before? That's just the derivative. Our formula starts off from the distance formula, and we just play with it around a little bit to get the square root of 1 plus the derivative squared times dx. You can find an arc length for any of these that way. Well, how about that for an example? You just want to find the arc length of some nice little curvy little function there. You don't even need to know what it looks like. All you need to know is an equation or its derivative. So with this, plug it into our function up top. Take a second to find the derivative and actually plug it in. Go ahead. Well, there it is. First you take the derivative. Then you say the square root of 1 plus the derivative squared. That's the setup. That's how you do it. It's that easy. Arc length is just a formula. If you can find the derivative, you're in great shape. And by the way, that'd be nasty to plug the numbers in, but it would give you the arc length. Yeah, so the setup is where it's all at. Can you set it up properly? Let's take a look at another different sort of problem. Now this was a puzzler they put on an AP question many years ago. By many, like 5 years. This was part C. This was the last part of an FRQ. They're having you find areas between these functions. The integral of the top minus the bottom. I think there was even maybe a volume thrown in, but part C said find the perimeter. Now, you didn't even have to get the answer. You just had to set up the equation to do it. So you can tell there are 3 different lengths there, and you kind of need to know a little bit about those lengths to be able to deal with this. First off, where do these intersect? When x is equal to 1, what does this graph equal? How high does it go? You kind of need to know that intersection point. So when x is 1, I can plug 1 in here and I find out that that length is just e. When I plug 1 in here, I find out these 2 graphs are going to intersect at 1, -2. So now it's pretty easy for me to tell that this length right here is a length of e. This length right here is, well, a length of 2. The top minus the bottom. You could even say, if you want this entire length, take the top value minus the bottom, you get e minus -2. So you know that your perimeter, that right-hand side, is e plus 2. Okay? Use a little bit of the same logic as we run out of time. And by the Pythagorean theorem, since this is 1 unit across, we can use the Pythagorean theorem to find out this is the square root of 5. But then the last part. As we run out of time, take the derivative of this function. And then to get the perimeter, or the arc length, 1 plus the derivative squared.